All right, so I want to review one of the types of problems on the last sheet of stuff that we did right before break. Make sure we're all on the same page with that. And then we'll get into the new stuff on the new handout that I just gave you. Before we start, though, I did put a Moodle quiz in for tomorrow night, due tomorrow night. It'll be over section 3.6, which is the rational function stuff. So make sure you go back and review that. That's the main reason why I'm doing it. Make sure you go back and review rational functions that we talked about. That was the first section we talked about from the, right after the last exam. Okay. So section 3.6. Not this stuff. This is the rational and polynomial inequalities. This is the section before that. All right. It'll open up right after class. It'll be due at 11:59 tomorrow. Okay. All right. Anyway, let's talk about this one. So we've got this rational inequality. Remember, for both your polynomial and your rational inequality, what do we need to make sure is on one side of your inequality? You need to make sure a 0 is on one side, right? If it's not all on one side to start with, you need to make sure that everything's on one side, right? Okay. Once we've got a single fraction like this, what do we want to do next? What's your first step before you try to do anything else? Yeah, factor it, right? That's the next thing you want to do, right? So let's see if we can factor this. Factor the top and factor the bottom. How does your top factor? Good, x minus 3 times x minus 3. How does the bottom factor?
X minus 3, x plus 2.
I think that would give you a... This is yeah, x plus 6 and x minus 1. Yep. Okay. There we go. All right. So remember, that's your steps for rational inequalities. I'll write them off to the side again. Get 0 on one side. Get a single fraction. Right? Move everything to one side, get a single fraction. The next step is to factor top and bottom. Why did we factor? What does factoring help us find? What does the factoring stuff help you do? Yeah, they give the zeros and the asymptotes, right? It tells you when the function is equal to 0. It tells you when the function has asymptotes. Where is this going to equal 0? When does a fraction equal 0? What do you look at? Do you look at the top or the bottom for when it's equal to 0? The top, right? Look for when the top is 0. When's the top equal to 0? 3? Good. So the numerator is 0. When x is 3. We look at the denominator is 0. When does that happen? Good, negative 6 and positive 1. So your next step here is find when the top is equal to 0 and when the bottom is equal to 0. Why do we look for those? Remember, we're trying to figure out where it's positive. And we talked about this before break. We're trying to figure out where it's positive. Where it's equal to 0 is where it crosses the x-axis. Where the top is equal to 0 is where the function crosses the x-axis. Where the bottom is equal to 0 is where we have vertical asymptotes. And those are the only places where you can change from positive to negative or vice versa. Those are the only places where you can change sign. Okay? That's why we're interested in those values. Because we're trying to figure out where it's positive in this case. So I want to know on what intervals it's positive. So what we're going to check is those different intervals and take those test points. If it's positive at a test point, it'll be positive in that whole interval. Likewise, if it's negative at a test point, it'll be negative on the whole interval. So our next step then is to make our table. With intervals and test points. What intervals are we going to look at in this case?
The jump from the 0 is negative 6 and 1.
Okay, say that again.
Negative 6, 1, and 3.
Okay, so those are where they break, right? So what's the first? What interval are we going to look at first then? Yeah, negative infinity up to negative 6, and then negative 6 to 1, 1 to 3, 3 to infinity. Good. So again, those points, the negative 6, the 1, and the 3, are the only places where the function can change sign. Either it goes from negative to positive or vice versa as it crosses the x-axis, or it jumps across the asymptote. That's the only places where it can change. Okay? That's why we found those first, because then that gives us our breaking points for our intervals. The next part is probably the easiest part of the whole problem. Pick a test point, right? So you got to pick numbers in here. So pick something in the first interval. Negative 7. Something in the next interval. 0 works, right? The next interval, 2. The next interval, 4, right? Doesn't matter what you pick as long as it's in there, right? Now we plug it in. Do we care what the value is? No, we just care about what the sign is, right? Whether it's positive or negative. All right, so plug negative, go back up to your factored form is probably the easiest thing to do. Go right here. When you plug negative 7 in, what do you get for those two factors? Are they negative or positive? They're both negative, aren't they? You'll have a negative, change back over to black here. You'll have a negative times a negative on top. How about on bottom?
Negative times a negative.
Negative times a negative. So the whole thing is positive. Good. If you need to plug it in the calculator and get a value, that's fine, but do we care what the value is? No, we just care about the sign, right? That's why I'm just keeping track of the negatives and positives. All right, how about when you put in 0, what do you get on top?
Negative times negative.
Negative times a negative. On bottom, you get
Positive
times a negative. So the whole thing will be negative. Didn't leave myself much room for the next two. Right a little small. I'll just zoom in a little bit. When you plug in 2, what do you get? Negative times a negative over positive times positive. And so the whole thing will be positive. Finally, the last one. I think everything's positive, isn't it? So you get positive when you're done? Now, going back to the original problem, what are you looking for? The positives or the negatives? The positive, right? Because it says greater than 0. All right. So what do we get for our solution then in this case?
The intervals, right?
Yep.
So negative infinity to negative 6.
Good.
And then 1 to 3.
Okay.
And 3 to infinity.
Good. That's a good question. That's what I was going to ask. Can we just do from 1 to infinity? All right. So are we okay with those intervals there? Why did I use parentheses, by the way?
Oh, because we don't want to include the
Yeah, that's not equal to, right? It just says strictly greater than 0. Now, even if I had been an equal to sign, would you have included the 6 or the -6 or the 1? Even if it had been an equal to, would you have included -6 or included 1? If there were an equal sign, would you include those?
No.
No, why not?
Because it has to be greater than 0, not equal to. Can't be equal to.
Okay, so I'm saying if there were an equal sign, if it were greater than or equal to, though, would you include say, -6 and 1? Where did the -6 and the 1 come from? The top or the bottom?
Bottom.
The bottom. Do we want to include anything ever that comes from the bottom? No, because what does that make it? It makes it undefined, right? Because I can't divide by the 0. Okay. So it doesn't matter if it were equal to or not. You would not include the -6 or the 1, right? So like Elliot had said here, could we just do 1 to infinity? In this case, the answer is no, because why?
Because it's on the denominator.
Well, the 3 though. The 3 came from the numerator. Why can't we include the 3? What tells us not to include the 3 here? Just the greater than, right? Because the 3 actually makes it equal to 0. So you can't just replace that with the 1 to infinity, because I need to omit the 3 because of the not equal to. All right. Does this process look familiar? I know it's been a little over a week, but does the process look familiar? This okay? All right, so let's go on to some new stuff then, which is a different type of function. So building a catalog of functions, if you will, that we deal with in different applications. So switching over to chapter 4 now, we're getting away from polynomial and rational functions and coming up with a new type of function that we refer to as exponential functions. Pardon me. And then we will talk about the inverses of these things in a couple of days. So what do we mean by an exponential function? Well, every type of function that we've talked about so far, we've had like a polynomial function or just a very easy polynomial function. When you've had f of x equals x squared, where's the variable? Is it in the base or in the exponent?
The exponent. Oh, the base.
The variable's in the base here, right? The exponent's a constant, isn't it? And every type of function that we've dealt with so far, if it's had an x, the x has always been down on the base, right? Okay. For exponential functions, we're going to flip that, okay? So for an exponential function, when we say we have an exponential function of base a, what we want is our function f of x has the form f of x equals a to the x. Now we do want to make sure that a has a couple of certain properties. We don't want a to be negative. We also don't want it to equal 1. And let's talk about that for just a second. We'll talk about that in a second, I should say. Let's go back to the form of the function. I have this a, but this a is just representing a number. So notice in this example where I'm asking us to sketch a graph here, the a would equal 2. Where the variable is up in the exponent. That's what makes it an exponential function. It's telling us that the variable's up in the exponent rather than in the base. So for exponential function, it kind of flip-flops that x squared idea, right? For x squared, the x is in the base, the 2 is in the exponent. This is what the exponential functions, it flip-flops it. Okay. All right. Let's talk about why we want to make sure we have these two conditions. Okay. Let's do the a is not equal to 1 first. If your a were equal to 1, what would that simplify to? It'd just be a 1 all the time, right? That's a constant function, isn't it? That's not what we want exponential functions to be, okay? So that's why we throw out the 1. We don't want it to always just equal 1, okay? Why do we want a to be greater than 0? Well, what if I tried to do something like -1 to the x power this way?
Just be the positive of it Well, no, because then I.
Okay. Well, let's see what happens. What would happen if I put a 1/2 in? What does a 1/2 power mean again?
Makes it 1 over -1.
That's if you do a negative exponent, right? The negative tells you to flip it upside down. What does a fraction exponent tell you to do? That's again if you have a negative exponent in there. Yeah.
Square it.
Not square it, but
root.
Yeah, this tells you to do what root to take, right? That will tell you to do the square root of -1, right? What's square root of -1 equal to? I. Now, what we want are what we refer to as real value functions. Is this a real number? No, it's a complex number, right? This is not a real number. And we don't want complex numbers to come out. Okay? So that's why we don't want anything negative here. Okay? We don't want any negatives because that's going to cause domain issues. Okay? So the first part, this a is greater than 0, is to make our domain be everything. So we don't have any domain issues. The second part is so that we don't get a constant function. Okay? That's why we have those two conditions. All right, so let's play around with these exponential functions a little bit. It's a new type of function. In math, usually if you come across a new type of function, the first thing you want to do is, what does it look like graphically? Let's see if we can get a graph. Okay? So in this case, we'll just make a table. We'll pick some x's, get out some y's. And I'm just arbitrarily going to pick some numbers for x. So let's do like a -2, a 1, a 0, a 1, a 2. And then we'll play connect the dots. Okay. Again, we're putting this in the exponent, right? So when I put -2 in for x, I get 2 to the -2, because I'm going to put the -2 up in for the x. Now, we just talked about this a second ago. The negative sign tells you to do what? The negative tells you to do what with the expression? Flip it, right? Make it move to the denominator. And then what is 2 squared? 4. So we get 1/4. All right, the negative tells you to flip it upside down. And we still just square it at that point. What do you get when you put in -1? 1/2, good. Anything to the 0 power is going to be 1, good. Yeah. Technically, 0 to the 0 power is undefined, but everything else to the 0 power is 1. Okay. 2 to the first is going to be 2. 2 to the fourth will be, 2 to the squared will be 4. Good. There. So now let's plot some points here. When x is -2, we had a y value of 1/4. When x was -1, we had a y value of 1/2. X is 0, we had a y value of 1. 1, 2, 2, 4. So plot of the points. Now we'll play connect the dots, but we need to be a little bit careful when we connect the dots. In particular, if I come out to the left, am I ever going to cross the x-axis? No. It will get really, really close to the x-axis, but we're never going to cross it, right? Because remember, a negative exponent doesn't tell you to make the number negative. It says flip it upside down, right? All right? Okay? So we'll get really, really close to the x-axis, but we'll never cross it. So we'll come this way and go up through these points this way, and then it'll get bigger that way. And that gives us a nice little graph of 2 to the x. That okay? Work on the next one for a minute, the next graph, and then we'll compare the two. So that was g of x equals 1/3 to the x power. Do the same kind of idea. Make a table of points, table of numbers, I should say. Get some ordered pairs, and see if you can play connect the dots.
Calculator. Damn. Calculator. Shoot.
You ready to chat? Yeah. All right. So I just picked -2, -1, 0, 1, and 2 again. Okay. What happens when you put -2 in? What do you get out? 9. So why do we get 9? So again, we get 1/3 to the -2. The negative tells you to do what? Flip it. So you get 3 squared, which will give you 9. Okay. What do we get when we put in -1? And we'll get 3 to the first, right? We'll just get 3. And remember, again, the negative just tells you to take the reciprocal, right? And then you can simplify the power after that. 1/3 to the 0 is going to give you 1. 1/3 to the first is just 1/3, and 1/3 squared is 1/9. That okay? All right, so let's plot some things here. We've got the point -2, 9 is up here. Negative 1, 3 is here. 0, 1 is here. We got 1/3, 1/9, getting closer to that x-axis again. Okay. And so coming this way, I missed, but that's all right. Looks like that. So you have something similar drawn? All right, so let's compare these two and see what similarities and what differences they have. So I'm going to shrink it. It's a little bit small now, but I want to get them both on the screen at the same time here. What do you notice for, well, what's one big difference? What do you notice?
They're just opposite.
Yeah, they're flipped around, right? I've got the first one's going up and to the right, the second one's going down and to the right. That's a big difference, right? But what about some similarities? Can you tell me some things they have similar?
They both do not touch the x-axis.
Okay, good. They both don't touch the x-axis, but they get really, really close to it, don't they? This gets really, really close here on the left-hand side. This gets really, really close on the right-hand side. What else do they have in common? The same y-intercept. They cross the y-axis in the same spot, right? Good. They have the same y-intercept. The other thing I notice is, do we have any holes? No. So they're continuous everywhere, right? The domain is everything. You know, we have domain all real numbers. And again, remember we said we wanted to make sure we had that, and that's why we restrict our base to be positive. Make sure there don't have any domain issues. Okay. All right. So let's see if we can summarize some of that stuff. And this is where we're going to do the similarities and differences thing. We said we saw no holes. So our domain here is going to be all real numbers, and it doesn't matter what the base is, right? How about the range? What do we notice for the y values? Let's go back up to my graphs again here. Here was the graph of the second one. Here's the graph of the first one. What do you notice about the range?
It does not include 0?
Doesn't include 0, but it includes everything that's what?
Upwards. So
Yeah.
infinity.
Up to infinity? Good. So doesn't include 0, but goes off to infinity. So we would have the interval from 0 to infinity, and 0 would not be included. What was that y-intercept? Good. So we have the point 0, 1 there. Were there any x-intercepts that had ever actually crossed the x-axis? No. Good. None. Again, didn't matter which picture we looked at, did it? Okay. How about horizontal asymptote? Do you see, go looking at my graph again, do you see a horizontal asymptote?
No.
Do you see a horizontal line the graph gets close to? Yeah, the x-axis does, right? Yeah, it's horizontal. Good. Yep, that's all right. Horizontal. Yep, and how about this one? Does that one have a horizontal asymptote as well? Yeah, it's just the other side, right? Good. So we get a horizontal asymptote of y equals 0. Now, granted, there's no vertical asymptote. You're exactly right, but there is a horizontal one. All right. Notice that those 5 properties are true no matter what the base is, as long as it's positive. Okay. What about increasing and decreasing part? All right, so let's go back up to my graph. Would we say that this function is increasing or decreasing? Decreasing, right? Because it's going down to the right versus the other one that is increasing. So that's a difference, right? We notice that difference right away. One is increasing, one's decreasing. What do you think we should look at for increasing or decreasing? Well, let's remember here. What did this negative sign tell you to do? Flip it, right? When I flipped this one, we made an honest to goodness fraction, something that was smaller than 1, right? Okay. Over here, what happened when you flipped it? It made it not a fraction anymore. It made it bigger than 1, right? Okay. So something's happening there at 1, right? So we notice that this thing is going to be increasing all the time. if your base is greater than 1, and it'll be decreasing all the time if your base is between 0 and 1. Think about it this way. If you've got a number that's bigger than 1, and I put in bigger and bigger powers, the number is going to get bigger and bigger, right? 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th gets bigger and bigger, doesn't it? If I put in something that's smaller than 1, and I get bigger and bigger powers, it's going to make it smaller and smaller. 1/3, 1/9, 1/27, and so on. So there's our big difference. It's increasing if the base is bigger than 1. It's decreasing if the base is between 0 and 1. What we're going to be most interested in, at least from my perspective, is what does the basic shape look like? What I mean by that is, what do the graphs look like based on the base? Okay, so we'll have 2 different possibilities, but the 2 different possibilities are going to be represented by the 2 examples that we did. Okay, we know that they all have a y-intercept of 1. We know that they all have a horizontal asymptote at x or y equal to 0. The only difference is whether it goes up or goes down, right? If the base is bigger than 1, which way does it go? Oh, up to the right or down to the right? Up and to the right, right? So this one's going to go this way, like so. The other one's going to be flipped around. The other one's going to go this way. Now, how steep they are depends on what the base is. The bigger this base gets, the steeper this would be. So what I mean by that is if you did, say, 5 to the x power, that's going to be steeper than 2 to the x will be. This gets steeper the smaller this number gets. But generally speaking, they have this J-ish shape or a backwards J shape, depending on which way you want to look at it. That okay? All right. So what we can do with these is problems like what we did back at the beginning of the semester with transformations. So we'll go through one together, and then I'll turn you loose on the last one, and we'll chat about both. So looking at this one, we've got y equals opposite of 2/5 to the x power plus a 1. So what we want to do here is identify a base graph and identify the transformations that have been done. Okay? The base graph gives us the basic shape, and then we'll transform it to what we have for the function that we're given. What function do you think we should use for a basic shape? What do you think we should use for our base graph? We're going to try to identify the exponential function we're going to use. What do you think we should use? Yeah, and which function would that be then in this case, if we want to actually write it down?
0 is less than 1 is less than 1.
Oh, I'm just talking about that specific function. Which function are we looking at? But you're right. Remember, like when we had x squared plus a 1, we used x squared, right? So what do you think we're going to use for our base graph here? Ignore what okay, let's try it this way. What transformations do you see?
Upwards 1.
Goes up 1 and it's flipped. About which axis?
The axis.
The x-axis, right? So ignoring those transformations, what will we use for our base graph? Yeah, the 2/5 to the x, right? Yeah, exactly. Okay, so that's what I meant by identifying what the base graph would be. Our base graph is going to be y equals 2/5 to the x. And now identifying what the basic shape of that looks like. Is that one going up or down?
Down.
Down, right? So it looks something like, I'm not going to worry too much about the scale. I just want to know what it looks like. It goes down and to the right, and we cross that y-axis at 1, right? We agree? Okay. All right. You told me the transformations already. What are the two that you see?
Yeah.
So that negative tells you to...
Flip about x-axis.
Good. That one's a reflection about the x-axis. And the second one is going to be up 1. Right? Those are the two that we see. Remember doing, I know it's been a little bit, but remember doing these? Okay. So reflected about the x-axis. Makes it look like that. Ish. We agree? Okay. Now when we shift it up 1 unit, where does this point right here go?
0.
Goes up to 0. Good. What else is going to get shifted up?
Rest of the graph.
In the whole graph. Oops. Didn't mean to do that. There, okay, there we go. So that is going to get shifted up here. What about that horizontal asymptote? It becomes at 1, right? So we're going to get a horizontal asymptote right here. And then that helps us graph the function, doesn't it? Like that. All right, so this one will be your final. Notice when we shift it up or down, that asymptote's going to go with it, right? Okay. Now again, all I'm looking for is basic shape, right? The basic shape for our exponential, its a base is less than 1, so it's decreasing. We still cross the y-axis at 1, and we have that horizontal asymptote at y equal to 0, right? That's our basic shape. You can make it a little more exact if you want to put in the numbers, right? Mine's actually not too bad here because it really does go through 2.5 here. But at that point, then you just want to do your transformations, reflect it and shift it up. What questions do you have on this one? Work on that next one, and then we'll chat about it. Ready to talk about it? Yeah. All right, what do you identify as the base graph here? Y equals 3 to the x. Good. So the base graph is, remember, the exponential, the form of a basic exponential, remember again, is a to the x, right? Nothing subtracted or added to the x, nothing multiplied, nothing's, right? Literally, that's the base, or the basic exponential idea. So that's what I want to identify as our base graph. Okay. Using that as a base graph, do we go up and to the right or down and to the right? Up and to the right, right? Because the base is bigger than 1. So our base graph should be going this way. Something like that. Okay. Now let's identify what transformations have been done. What transformations do you see here? I see a shift down too. What else do we see? Yeah, there's a shift right too as well, all right? Okay. What's telling you the shift right? Yeah, the -2 up here. Notice that's a little bit different than what we've seen before, isn't it? That's why I want to do an example like this one. Remember that we have transformations that affect the x's and we have transformations that affect the y's, right? We have horizontal transformations and we have vertical transformations. We identify those by what's being done on the inside of the function versus what's being done on the outside of the function, right? Notice that in the previous example, both of our transformations were being done on the outside of the function. It was pretty easy to identify, right? We had those two transformations, the negative sign here and the +1 here. Notice, though, that this -2 up here, that's technically inside the function, right? Think about it this way. If I had f of x equals 3 to the x, then f of x -2, remember this means take out the x and put in what you see in the parentheses. That's why this -2 is inside the function. Notice it's inside the parentheses here. Okay. Anything that happens on the inside of the function affects the x's, and that's why it's a right shift of 2. Does that make sense? Okay. So let's do it step by step here. If I shift right 2 units, does that change your horizontal asymptote at all? No. Shifting left or right is not going to change the horizontal asymptote. All we do is pop this point over here and redraw. Like so. So that would be step 1. Now we shift down 2. Where does that horizontal asymptote go to? We get -2 down here, right? And then this point ends up at -1. And we end up with the same graph, just shifted down. Does that make sense? We okay with that? All right. So that's our basic introduction into exponential functions. We'll do a specific type of exponential function next time. It's called the natural exponential function. We'll talk about what that means. Don't forget, there's also a Moodle quiz due tomorrow night at 11:59. There's over rational functions, section 3.6. Have a good one. We'll see you on Wednesday, if not before.